Hi, my name is Manish Gupta, and in this video, I'm going to talk about self-instruct, which is a way of improving your instruction fine-tuning using self-generated instructions. So let's get started. Why do we need a self-generation method for instructions? Okay. So as we know in today's world, large instruction-tuned language models are getting very popular. They actually generalize zero shot to many new tasks and therefore are very generally applicable. Now, these developments basically are powered by two important components. One is large pre-trained language models, and the second is human-written instruction data. For example, prompt source, which has been used for instruction tuning T0, and supernatural instructions or super NI. Now, these human-written instructions are often very limited in quantity, diversity, and creativity. So if you ask people to write instructions, they would typically write about head tasks, right? About popular NLP tasks. They would not really care about the tail, and therefore diversity is also rather limited. And therefore, we need an automated system so as to actually come up with these instructions. Self-instruct is one such system which I'll talk about in this video. It's a framework for improving the instruction following capabilities of pre-trained language models by bootstrapping off their own generations. Okay, the aim of self-instruct is to generate instructions, input and output examples from a language model, then filter the invalid ones or similar ones before using them to fine-tune the original model itself. It's called self-instruct because it is more like self-training, right? So essentially, you want to use the same model so as to generate more instructions, input and output examples, and then, after filtering some of them, you want to use the remaining ones, the good ones, so as to fine-tune the original model itself. So how does self-instruct work broadly? This diagram actually shows you the entire self-instruct philosophy. So here, there are four components to self-instruct: generating task instructions, determining if the instruction represents a classification task, instance generation with either an input first or output first approach, and then fourth is filtering low quality data. I will go into details of each of them in the next few slides, but let's detail it out a little here itself. Right. So self-instruct in this particular work, in fact, the authors actually did self-instruct on GPT-3 model. They started off with a seed set of 175 tasks, each with one instruction and one instance per task. So that's your original task pool to start off with. You take a language model, for example, GPT-3, and then ask GPT-3 so as to generate more instructions which are similar to the ones that you already have in the seed tasks. Right? For example, give me a quote from a famous person on this topic. Now, the second step, so that's about the first step, generating task instructions. The second step is about determining if the instruction represents a classification task or not. You use a language model with a particular prompt to do that as well. Now, after that step is done, you know whether the task instruction is about a classification task or about a non-classification based typical generation task. Right? Now, if it's a generation, if you figure out it's a classification based task, you actually do generate the instance in what is called as the input first kind of a method. And then if it is not a classification instruction, you basically generate using an output first kind of an approach, the input and output instance using the output first approach. We'll talk about what is input first and output first approach in the next few slides. Lastly, you filter out low quality data, whether it is low quality instructions or low quality instances, and add the remaining ones to the overall task pool. This is how you keep iterating. So you keep iterating over these four steps several times until you get a rich task pool. Let's detail out these things. So first, let's talk about how does self-instruct work from an instruction generation perspective. The first step is to generate instructions, right? So as we discussed on the previous slide, we start off with 175 tasks, one instruction and one instance for each task. Here is a prompt. Here is a simple prompt which is used for generating new instructions. So in each of these prompts, 8 existing instructions are randomly sampled from the 175 task pool. Or the task pool may become larger over iteration. So whatever is your current task pool, you sample 8 instructions from them, and you use them to demonstrate. So this is a few short prompt. You demonstrate that this is how a task looks like, and your instruction looks like. Generate more instructions of this kind. Right. So the model is allowed to generate instructions for new tasks until it stops its generation or reaches a maximum sequence length. Of the 8 instructions are provided here, 6 are from the human written tasks from the original 175 tasks, while the remaining 2 are from the model generated tasks in previous steps to promote diversity. Of course, in the first step, there is no model generated task, therefore you use all the 8 from the human written ones only. Now, once you have gotten the instructions, you want to figure out if these instructions could correlate with a classification task or a non-classification task. So for that, again, you prompt the language model in a few short ways so as to understand if it's a classification task or a non-classification one. In their particular case, they used 12 classification instructions and 19 non-classification instructions from the seed tasks so as to generate this few short prompt. So this few short is really large in the senses. And you can see some of the examples here. So the prompt is pretty simple. Can the following task be regarded as a classification task with finite output labels? And then there are several few short examples. For example, given my personality and the job, can tell me if I would be suitable. Is it classification? And the answer is yes. Give me an example of a time when you had to use your sense of humor. Is it classification? The answer is no, right? So there are several such examples you pass on, and then finally you give your current task instruction, and the model should output yes or no, depending on whether the model believes it's a classification or not. Well, an interesting thing to note, they did not really use any chain of thought kind of stuff here, possibly because it's a simple enough task to do with not really requiring multiple steps of reasoning. Okay. Further, the next step is to generate the instances. You have the synthetic instructions now, task instruction, you know it's a classification task or not. Now you have to generate instances. And let's see how these instances are generated. Okay, so the idea is given the instructions and their task type, classification or not, you want to generate instances for each instruction independently. Okay. This task is, by the way, difficult, and this is also going to be done using the large language model. However, the model here needs to first understand what the target task is based on the instruction, right? Figure out what additional input fields are needed, and then, of course, generate those inputs and also, reason around and then get the output for it. Okay. So this is a fairly complex task, fairly complex thing for the model to do. Okay. Now you go to prompt with this format. So instruction, input, output, in context examples from other tasks. Okay, so here is how the prompt looks like. Come up with examples for the following tasks. Try to generate multiple examples when possible. If the task doesn't require additional input, you can generate the output directly. Okay, so there are several things to keep in mind. First of all, to do this instance generation, you write a few short prompt. So you basically give examples of tasks with their inputs and outputs. So you see there are several examples of tasks with inputs and outputs which are provided, and many more examples. And then you give your own instruction for the target task and ask it to come up with an input and output. Okay, so it's a few short prompt first, right? Second, you basically ask it to generate multiple examples when possible. So you don't really tell it to generate only one example. It can generate multiple examples. In fact, in the few shot itself, you basically give some cases where you give no examples at all. Well, you give an example. Sorry, you give either one example, right? Or you can actually give more examples. For example, here 2 examples are given in the same task, in the same few shot exemplar for that matter. Okay. Now, in some cases, the task may not require additional input, in which case you can generate the output directly. For example, this one, which exercises are best for reducing belly fat at home, you don't really require any input, and therefore the output is directly generated. However, there could be other tasks. For example, this one, sort the given list ascendingly. So in this example, you require an input and then you have an output. You require an input, you have an output, right? So some tasks require input and then the input should be provided. If tasks don't require input, directly the output can be provided. Okay. Now, this kind of an approach is called input first approach. So you ask a language model to come up with the input fields and then output, and that's how it is. That's how typically one would do it. However, there are problems with this way of doing things. In this way of doing things, the model can actually generate inputs biased towards one label, especially for classification tasks. So, for example, for grammar error correction as a task, it usually generates grammatically correct input and then just output saying yes. So that's a big problem. Okay. To avoid this bias towards the popular labels in that senses, these guys also propose something called as an output first approach. And this output first approach really applies for classification tasks. The idea is that you first generate the possible class labels and then condition the input generation on that class label. Okay. So For example, is this sentence grammatically correct? And then you would say no, and then you generate an example of a not grammatically correct sentence. I mean, using, of course, the same language model. Okay. Here is another example of an output first generation. You give, in fact, of course, the few short examples also need to be given in that way so as to motivate the model to do the output first approach. Okay. Classify the sentiment of the sentence into positive, negative, or mixed. And then you say class label is mixed. So then sentence, with that mixed class label, now the model has to basically condition on that and generate a sentence which basically shows you a mixed sentiment kind of an answer. Okay, so that's that. Okay. So overall, after you've done these 3 steps of task instruction generation, classification or not classification, and also figuring out input and output, you have to next do filtering and post-processing so as to eliminate instructions which are not good or tasks which are not good, and also eliminate those instances which are not good. So you can basically remove those instructions if the Rugel similarity with any existing instruction is less than 0.7. Okay. And this is done for diversity purpose. You don't want to have redundant tasks in that sense, or very similar tasks in that senses. You also want to remove those instructions which contain some specific keywords like image, picture, graph, because LMs, large language models are text-based models. They can't generate images, pictures, or graphs, and cannot really work with them. Right? You also remove those instructions which are too long or too short, of course, right? So next, you can also filter out instances. So you remove those instances that are exactly the same or those with the same input but different outputs. You also remove those instances which are repetition of where the output is a repetition of the input. So these are all obvious ways of filtering out not useful instructions or not useful instances. The interesting part to note is that after all this is done, you take this data and you fine tune your GPT-3 model and you call it a GPT-3 Self-Inst model. Now, this GPT Self-Inst model, the authors actually fine-tuned on their dataset, the GPT Self-Instruct dataset that they created using this methodology, using the OpenAI API itself. That costed them just $338. So fine-tuning GPT-3 models is not an impossible task. It's very much possible and very much practical. So they fine-tuned 2 epochs over their data and just took like $338. It's pretty cheap in that sense. Overall, their data across several iterations consisted of 52K different tasks and 82K instances around those tasks. They, of course, experimented with the GPT-3 large language model, the DaVinci engine. Now, here is a little bit of analysis about their data. So here are some examples of the tasks that they generated. Given an address and city, come up with the zip code, and here is the input and the output is this. Okay. I'm looking for a job and I need to fill out an application form. Can you please help me complete it? There is an input and then there is some output which is generated. So these are all examples of interesting tasks. Write a letter from a perspective of a cat, and here's a letter which is written, no input required here. Okay. So these are kind of examples which are there in this self-instruct data set. Self-instruct dataset is basically just like any other dataset for instruction fine-tuning. It's just that it's automatically created rather than human generated. Okay. Here is some more insight into what kind of tasks they are. So write a paragraph, write a letter, write an essay, write a function. So this basically represents 20 frequent verbs that were there in their dataset, and then frequently following nouns after them. So give examples, give list, give set, give advice, or find a number, find word, find sentence, find a way, and so on. Right. Now, these are just a few of them. In fact, these 20 verbs indicate only 14% of these examples. So basically saying that the dataset is pretty diverse in terms of the kind of task that it has. Okay. Now, they also got some manual annotations done so as to figure out how good the quality of the data is. And here is the distribution of the quality review that was done. Does the instruction describe a valid task? 92% times, yes, it does. Is the input appropriate? 79%, yes, appropriate. Is the response a correct? Is the output a correct and acceptable response to instruction input? 58%, yes, it was. So 54% of the times, all the fields were completely valid, basically saying that the overall quality of the data set is pretty good. Okay. Now, having said all this, how does GPT-3 Self-Instruct perform, right? So basically, and as you see here, the performance is actually measured on the super natural instructions benchmark dataset in a zero-shot manner. Okay. Now you have in this comparison vanilla large language models, the T5 LM model, GPT-3 model. You also have instruction-tuned models without any super NI data being used, and there is instruction-tuned models with super NI data. Now, what's that? And we'll talk in detail about that as well. T5LM and GPT-3 models are standard models, no instruction tuning. Now, this is basically T0 model, which has been instruction tuned, remember, on prompt source. Now this GPT-3 model again trained on the prompt source, which is basically also used for T0 model. And then this is GPT-3 Self-Instruct, which has been instruction tuned on self-instruct data. And then this is the Instruct GPT-001 model, which has been instruction tuned by OpenAI on their own proprietary data, which is not disclosed at all. Right? Now, these are basically also sizes of these models. And then what you observe is that amongst all of these models, of course, Instruct GPT-001 is awesome, but then GPT Self-Instruct is also great. So amongst the publicly available instruction-based models like T0 or even GPT with T0 training, GPT-3 Self-Instruct performs really well. Comparison, if you do really right, so, compared to GPT-3, GPT-3 Self-Instruct does super awesomely better, right? So much, much better. An absolute 33.1% gains in terms of Rouge-L, large margin, right? Now, the interesting part is that considering the proprietary Instruct GPT data that OpenAI used was the GPT-3 model, which has been fine-tuned using now the publicly available self-instruct data, the performance nearly matches, right? It's basically 39.9 versus 40.8. So it's not too far. The other thing is that if you basically take TK Instruct model, which has been fine-tuned using Super NI data, and also GPT-3 model, which has been now fine-tuned, let's say, using Super NI training data, and then you take GPT-3 Self-Instruct model, which has been first fine-tuned using Self-Instruct data, and then further fine-tuned using Super NI data, what you observe is this one is the winning combination. So Self-Instruct model further fine-tuned on Super NI data improves the performance even more. So, you basically have 39.9 that becomes like 51.6. This is really good. Okay. Now, this is all automated evaluation, right, in some way. So therefore, what these authors did was also to come up with new tasks, so in a human way, and then evaluate on those tasks. So this is basically evaluation on standard tasks, which are there in the Super NI benchmark, which are popular NLP tasks, right? So how about coming up with interesting tasks like email writing, social media-based tasks, productivity tools, entertainment, programming tasks, which are not usually there in standard, benchmark data sets to measure, okay? So that's what they did. And then they also, got the output from GPT-3 Self-Instruct model and asked humans to judge them. They, of course, got output from various other models and asked humans to judge them. And what they found is that you see those results. So they asked humans to actually judge on ABCD for a point scale, where A basically means correct and satisfying response, and D basically means completely irrelevant or invalid response, and B and C are in between. You observe that vanilla GPT-3 performs really poorly. Most of their responses are invalid or irrelevant responses on these hard, or tailish intents of NLP tasks, right? On the other hand, as you do this instruction fine-tuning using T0 data or Super NI data or self-instruct with Super NI or just self-instruct itself, what you observe is that the overall number of good responses of the good tasks of the good outputs that are generated is much higher with GPT-3 self-instruct. In fact, GPT-3 self-instruct performs almost as close to OpenAI's Instruct GPT-001 model. Of course, there's a lot of room to cover to reach OpenAI's Instruct GPT-3003 model, but then there's good hope and good direction to believe that yes, we are reaching there. We are sort of or rather in this particular case, GPT-3 model just to fine-tune with self-instruct can reach there, can reach the Instruct GPT-001's accuracy to some level. Okay. Here are some of those responses. So this is the instruction and instance input. Give student tips on how to keep their nerves under control during class presentations. Here is the target response that was written by a human. And here is the GPT-3 self-instruct response. And then finally, the rating given by a human so as to say how good this response was. Right? So as you can see, this response is pretty good in that sense, right? So practice your presentation in front of friends and family. How do you, be careful but and not basically get very nervous when you're sort of presenting, during class presentation. These are good tips in general, I think. Yeah. And there are more examples. You can pause the video to actually look at these examples. Now, they also did some other experiments so as to identify if we need really large amounts of self-instruct data or small amount of self-instruct data is also okay. Right. So here on the x-axis, you see number of instructions, how much amount of self-instruct data was used by GPT-3, to fine-tune GPT-3 model. And here is percentage of responses rated as A, right? So they observed that, and here what you see 171 instances here, which basically means none of the self-instruct automatically generated data was used. Remember, 171 was the initial set of manually generated examples anyway. And then they increased the number of examples to 800, 6,400, 51,200, their overall set, right? What you observe is that as you increase the number of instructions, you see that there are consistent improvements as we grow the data size, right? However, it sort of flattens here, right? So essentially saying that if you essentially have just these many number of instructions, that is also good enough. You probably don't need to generate more self-instruct instructions. Okay, now that's one. The second thing is that they basically said that, hey, how about actually doing this, instruction generation, not from GPT-3, but from Instruct GPT. So they basically did the entire self-instruct dataset creation using Instruct GPT, not really the entire. In fact, they just generate the output field of these instances using Instruct GPT-003, right? So they still have the task instructions, the inputs being generated by GPT-3 model. However, they used Instruct GPT-003 so as to generate the output field. Now, using this, and you fine-tune GPT-3 model, instruct fine-tune GPT-3 model using this, what you observe is that you get significantly better improvements in accuracy. Yeah. So 44.4, the number of A's basically becomes 54.4. So rather than just having the number of A's as these 44.4%, you basically now have 54.4% of those outputs which are rated as A. Yeah, so that's a big win. Okay. In summary, in this video, we talked about self-instruct, which is a method to improve the instruction following ability of large language models via their own generation of instruction data. It sort of tries to eliminate the need for human generation of instructions, or instruction examples, and therefore helps us to generate instruction examples even for tail tasks. A large-scale data set of 52K instructions for diverse tasks is created as part of this effort. And then the GPT-3 model was fine-tuned on this data, which led to a 33% absolute improvement on super instruction benchmark data set over the original GPT-3 model. This approach is very much similar to self-training and knowledge distillation approaches. You can think of the approach as self-training, and therefore, in fact, it's called as self-instruct, because in some ways you're asking the model so as to generate instructions and inputs and outputs, and then train on top of that in an instruction fine-tuning manner, right? But there are differences as well, right? Self-training approaches were typically for supervised learning. This is basically instruction fine-tuning and so on. So there are differences, right? This can also be thought of as knowledge distillation, especially in this part where you basically took the output from Instruct GPT but 003, but then you tried to improve the quality of the GPT-3 model using those outputs. So in some ways, it's more like knowledge distillation, but then, well, there are differences from standard knowledge distillation philosophy as well. Okay, so that's it. So hope you liked the video. Thank you for watching. Connect with me on my LinkedIn or look at my research on my homepage. Thank you.